Welcome to Professor Vida Zohoori's lecture. We had hoped to hold these events in person, but are delighted to bring this to you online. And as restrictions ease, we hope to be able to deliver more lectures both online and in person. So details of other events will be made available in due course, so please ensure you follow the university for more information. These lectures are key to the university and are an excellent opportunity for you to hear about what is happening in our research community. They allow us to share the incredible work being done at Teesside University. Professor Zohoori will respond to all your questions via email following this lecture, so please submit any questions you might have to events@tees.ac.uk. I'll now hand you over to Professor Zohoori, whose lecture title is The Power of 1 in a Million, which is a discussion around fluoride exposure and retention in the body. Thank you for joining us, and we hope to see you at future lectures.
Hello everybody, and thank you for tuning in this evening. As Steve mentioned, I'm Vida Zohoori, a professor in public health and nutrition. By background, I'm a nutritionist and a dietitian. And in fact, my research journey started from my PhD at the School of Dental Sciences, Newcastle University, under the supervision of Professor Andrew Ragan. My thanks go to him for his extensive support during my PhD. I think I was fortunate to receive feedback on my work from international experts in the field, including Professors Neil Jenkins, Tommy Marthaler, and Gary Whitworth, as well as Dr. Ralph Duckworth. After graduation, I worked at Newcastle University as a postdoc research associate with Andrew, and then Professor Anne Maguire, before joining Teesside University in 2007 as a lecturer. I'm grateful to Andrew and Ralph for their continuous support and mentorship. It was during my PhD that I was introduced to the topic of oral health. Oral health is essential for maintenance of general health and well-being. Globally, almost 4 billion people are affected by oral diseases. Oral diseases are associated with significant pain and anxiety, acute and chronic infections, eating and sleep disruption, and impaired quality of life. Oral diseases impact every aspect of life, from relationships and self-confidence through to school, work, ability to interact with others, social isolation, and even reduced income. Dental caries or tooth decay is the most common non-communicable disease, which affects 60 to 90% of school children and most adults. In the UK, 25% of 5-year-old children have dental caries, and it's the most common reason for hospital admission of 5 to 9-year-old children, which puts significant cost on the NHS. For example, in 2015, more than £50 million was spent on tooth extraction in children. Dental caries can be easily prevented by good oral hygiene, diet, and usage of fluoride. Fluoride is the topic of my talk today. Fluoride is the 13th most common element in the Earth's crust. Naturally, it releases into the atmosphere through volcanic activities, and in less extent through human manufacturing activities. It returns to the earth through rain and deposits in land or water. Levels of fluoride in lakes, rivers, and wells is less than 0.5 part per million, or ppm. And in seawater, it's between 0.8 and 1.4 ppm. But water at the foot of volcanic mountains contain very high fluoride, even up to 2,800 ppm. Fluoride is considered a trace element because the body requirement for maintaining dental health is only a few milligrams a day. And because only small amounts are present in the body, only about 2.6 grams in adults, and more than 95% of the total body fluoride is found in bones and teeth. After ingestion, almost 90% of the fluoride is absorbed in the stomach and guts. The absorbed fluoride circulates in the body through blood and deposits in hard and soft tissue. And plasma fluoride concentration reaches its peak 20 to 60 minutes after fluoride ingestion, and returns to pre-ingestion levels during the following few hours. And more than 50% of fluoride is excreted into the urine. The history of fluoride started in the 1930s with epidemiological studies across 22 cities in 10 US states to understand the relationship between fluoride concentration in naturally fluoridated water and dental health. The first water fluoridation experiments started in 1945 in Grand Rapids by adjusting fluoride concentration of the water supply to the optimum level of 1 part per million, and hence the title of this presentation. In 1950, the US Public Service endorsed water fluoridation. And by 1958, the World Health Organization supported water fluoridation as a public health measure. Fluoridated toothpaste were then introduced to the market in the early 70s. And in 2009, EU regulations approved the addition of fluoride to foods, including milk and salt. In 2011, the US Public Health Service recommended lowering optimum water fluoride concentration to 0.7 ppm due to the contribution of other sources of fluoride exposure. Currently, more than 370 million people in 27 countries receive fluoridated water, and more than 1.5 million children, mainly in the UK and Chile, receive fluoridated milk in school. And more than 100 million people use fluoridated salt, mainly in Switzerland, Germany, France, and Latin America. Caries preventive effects of fluoride are mainly topical. Fluoride decreases demineralization of tooth enamel, increases tooth remineralization, and reduce the overgrowth of harmful bacteria. Fluoride also has some systemic effects. It incorporates into developing teeth during their growth, increasing the resistance of teeth to acid demineralization. Community water fluoridation is the controlled addition of fluoride at a level of 0.7 to 1 ppm to public water supplies. It's the most cost-effective policy for reducing dental caries. and has been considered one of the 10 greatest public health achievements of the 20th century. In the UK, the community water fluoridation schemes started in Birmingham in 1964, and by 1980, more than 6 million people received fluoridated water at a level of 1 part per million. In 2021, Public Health England recommended water fluoridation as a whole population intervention as it reduces oral health inequalities with a greater benefit for those living in more deprived areas. Several oral health surveys around the world, including the UK, showed the effectiveness of community water fluoridation in reducing dental caries. For example, the England Oral Health Survey in 2017 showed that the incidence of dental caries in 5-year-olds was lower in naturally fluoridated Hartley Pool, as well as artificially fluoridated North Tyneside and Gateshead, compared with non-fluoridated Middlesbrough and Sunderland. In 2000, a systematic review on the health effects of fluoride found a lack of studies that assessed natural versus artificial water fluoridation. Then a medical research council working group identified bioavailability of naturally fluoridated water versus artificially fluoridated water and of hard versus soft water as important topics that should be investigated. In an in vivo study, which I was part of, we assessed the bioavailability of different types of water. We recruited 20 healthy young adults, and over the 6-week experimental period, each participant took part in 5 experimental sessions with a different water consumed each session. We collected blood samples over a period of 8 hours before and after the participants drank the water. We didn't find any statistically significant difference between the artificial and natural hard and soft water. Although low levels of fluoride can prevent dental caries, excessive systemic ingestion of fluoride can result in dental fluorosis or mottled enamel. The suggested optimal fluoride intake to prevent dental caries is 0.7 to 0.05 to 0.07 milligram per kilogram body weight per day. However, an intake of more than 0.1 milligram per kilogram body weight per day can result in dental fluorosis. Therefore, fluoride intake, particularly in children, should be monitored regularly to minimize the risk and maximize the benefit. I should point out that the optimal and upper limit values of fluoride intake originated from early studies in the 40s when water was the only source of fluoride intake. Critical age for development of fluorosis in primary teeth is from 5 months before birth until 11 months of age. And in permanent anterior teeth, it's the first 5 years of life. To evaluate fluoride exposure, we need to have valid methods for fluoride measurements. In a study led by Indiana University, we were one of the 9 international centers to develop standard methods for fluoride analysis of biological and non-biological samples, including food and drinks. We then led a collaborative project to assess methods for determination of fluoride in microliter volume blood samples. The main sources of fluoride intake in children are diet and dental products. We conducted several exposure studies in children in the UK and found that toothpaste ingestion is the main source of fluoride intake in very young children. But by the age of 6, the contributions of diet and toothpaste ingestion to total fluoride intake become almost equal. In fluoridated areas, drinks, particularly tap water, squash, and cordials are the main dietary sources of fluoride. Whereas in non-fluoridated areas, food such as rice, pasta, boiled vegetables, and bread are the main dietary sources. To quantify fluoride intake, we need to know the fluoride content of consumed food and drinks. The current food composition tables don't report the fluoride concentrations of food and drink items. So over several years, we, in collaboration with Newcastle University, measured fluoride contents of more than 500 commercially available foods and drinks and published a unique fluoride database in 2015, which can be used by researchers, public health planners, and healthcare professionals to estimate dietary fluoride intake in a population. We were then commissioned by the Food Safety Authority of Ireland to measure a fluoride concentration of almost 200 food and drink items available in the Irish market. We added those data to our database and updated our database in 2019. We measured fluoride content of more than 200 baby foods and drinks and found that more than 70% of the products contained less than 0.1 microgram per gram fluoride, and only 1% contained a fluoride concentration of more than 1 microgram per gram. However, the interesting finding was that we noticed different fluoride contents in the same products depending on the manufacturers. For example, when we measured fluoride content of infant milk formula from 7 different manufacturers, we found a wide variation in the fluoride content. Currently, labeling fluoride content of food and drink products is not mandatory, but the findings from our study highlights the need for comprehensive fluoride labeling on food and drink products, particularly baby foods. To monitor fluoride exposure, one should be able to quantify total fluoride intake from all sources. To assess dietary fluoride intake, food diaries and duplicate plate methods are the 2 most commonly used methods. To assess dietary fluoride intake from food diaries, participants are asked to record everything they consume over 3 days, usually 2 weekdays and 1 weekend. Samples of consumed food and drinks are collected from participants and analyzed for fluoride content. In the duplicate plate method, participants are asked to prepare two similar sized meal portions, and one portion is analyzed in the lab for fluoride content. It's not quite practical to use these two methods in larger scale studies. For larger studies, a food frequency questionnaire is usually used, which gives a rough estimates of total fluoride intake. To quantify fluoride intake from toothpaste ingestion, the commonly used method is a questionnaire. But if precise information is needed, the most accurate method is to collect samples of expectorated saliva and toothpaste during brushing. In this method, we ask the child to brush their teeth based on their normal habits. We measure the weight of the toothpaste that the child puts on the toothbrush, and we collect all expectorated saliva, toothpaste, and rinse water during and after brushing. We measure the fluoride content of toothpaste and the fluoride content of expectorated saliva, and the difference between these two is the amount of fluoride that is ingested. So as you can imagine, this is quite a time-consuming method of measurement. The recommended amount of toothpaste for young children is a pea size, which is 0.25 grams. We conducted a study with 61 children and found that children use much more toothpaste than the recommended amount. As you can imagine, it's extremely difficult to quantify fluoride exposure. Therefore, recent studies have focused on finding valid fluoride biomarkers. Biomarkers of exposure are the actual substances or chemical metabolites that can be measured in the body or after excretion from the body. The suggested fluoride biomarkers are hair, saliva, nail and fingernail, toe and fingernails, and blood and urine. In a collaborative study, we investigated the relationship between a total daily fluoride intake and 24-hour urinary fluoride excretion for 212 children younger than 7 from 6 countries. We found a strong correlation between the two. We then developed a model to predict total daily fluoride intake from 24-hour urinary fluoride excretion. In 1999, the World Health Organization published a guideline for monitoring fluoride exposure in communities. In 2011, I was invited to the World Health Organization Technical Working Group meeting in Geneva to review the 1999 guidelines. The working group approved our experimentally based model to estimate total daily fluoride intake from urinary fluoride excretion data as the basis for the revised guidelines for monitoring fluoride exposure in children. And the new guidelines were published in 2014. Collecting 24-hour urine sample is also quite challenging in young children, especially those who are not toilet trained and wear nappies. We conducted a study in the UK investigating the validity of spot urine samples for estimating fluoride exposure. we found that a spot urine sample wasn't a valid biomarker of fluoride exposure, but found a strong correlation between total daily fluoride intake and fluoride in spot urine samples when corrected for creatinine excretion. Then we estimated urinary fluoride creatinine ratios associated with low, optimal, and excessive fluoride exposure for children. However, this study only looked at water fluoridation and conducted only in the UK. In 2019, we received funding to look at the usefulness of spot urine samples corrected for creatinine excretion for different fluoridation schemes, including water, salt, and milk. This is a collaborative project with Sao Paulo University in Brazil, University of El Bosque in Colombia, and University of Talca in Chile, and Newcastle University in the UK. However, due to the COVID-19 pandemic, the project has been suspended for now, and we are hoping to be able to resume activities soon. When it comes to biomarkers, it's not just their validity, but also their acceptability that's important. We conducted a survey and asked adults about their willingness to provide samples of their own urine over 24 hours. More than 60% of the participants said that they were happy to do so. But when we asked the same adults if they would be happy to collect urine samples from their children over 24 hours, only 40% were happy to do so. Among the biomarkers of fluoride exposure, blood was the least acceptable option, and nail clippings were the most acceptable method. We collected samples of different biomarkers from almost 100 adults and identify plasma and toenails as potential biomarkers, apart from urine, 24-hour urine. However, as blood collection is quite invasive, it's not suitable for monitoring fluoride exposure in children. That's why most studies have focused on nail clippings. However, the findings of these studies are conflicting, and more research is needed. We know fluorosis is a multifactorial problem. There are many factors such as nutritional status and physiological factors that could affect fluoride metabolism and fluoride bioavailability, and consequently fluoride retention in the body. When the amount of ingested fluoride is higher than excretion, the body is in a positive fluoride balance. But when the excretion is higher than intake, the fluoride balance is negative. Several factors could affect fluoride absorption and excretion. For example, a diet high in fat decreases the rate of gastric emptying and therefore increases fluoride absorption. But a vegetarian diet increases urinary fluoride excretion, and a diet high in some elements such as calcium increases fecal excretion of fluoride. Excessive systemic fluoride intake has been suggested as the main factor for the development of fluorosis. In some parts of Tanzania, dental and skeletal fluorosis are major public health issues, even in areas with negligible amount of fluoride in water. We led a team funded by the Royal Society to visit the affected areas in Kilimanjaro. We visited the affected families and tribes and collected samples of water and soils. Our visit identified several factors as potential explanations for fluorosis, including weaning age, physical activity, malnutrition, genetics, altitude, and local food. In particular, magodi, a food tenderizer which is used very often by locals, which has a very high fluoride content. We investigated the effects of altitude on fluoride metabolism. We recruited 100 children and their parents in low and high altitude areas in Nepal and assessed their total daily fluoride intake, 24-hour urinary fluoride excretion, and fluoride concentrations of nail clippings. Our results show that higher altitudes lead to decreased urinary fluoride excretion and consequently increased fluoride retention in children. But altitude had no significant impacts on the levels of fluoride excreted by adults. In another collaborative study, we looked at the effects of exercise on fluoride metabolism using both animal and human models. The animal study was conducted in Brazil with a strain of mice susceptible to fluorosis. The animals were categorized into 3 groups. The control group didn't receive any fluoride and didn't perform any exercise. But groups 2 and 3 received 50 ppm fluoride, which is equivalent to 10 ppm for human. Group 3 had a daily routine exercise. We found that mean plasma and bone fluoride concentrations were significantly higher in groups 2 and 3 compared with the control group. But exercise had no effect on fluoride in plasma and bone. An interesting observation in our study was that exposure to high fluoride resulted in lower weight gains in animals. The human study was conducted in the UK. We recruited healthy young adults, and each participant attended 4 randomly allocated experimental sessions, including 1 no exercise session and 3 exercise sessions at light, moderate, and vigorous intensities. We collected blood and urine samples from each participant before and after exercise. We found a lower urinary fluoride excretion and higher plasma fluoride concentrations with moderate and vigorous intensity exercise. These results suggest higher fluoride retention with moderate and vigorous exercise. However, our study was limited to 9 participants, and therefore more studies with larger sample sizes are needed to confirm our finding. We also looked at the effects of weaning on fluoride retention in babies. We assessed infants living in fluoridated and non-fluoridated water areas in the Northeast. We collected dietary information using 3-day food diaries and collected all used nappies over a 48-hour period, and measure fluoride intake as well as fluoride excretion through feces and urine. Studies conducted in the 70s and 80s reported a fecal fluoride excretion of almost 10% in infants. However, our study showed that on average 3% of the ingested fluoride was excreted in feces, with a range from 1 to 6%. We also found that breastfed infants had negative fluoride balance, but in weaned infants, a relatively large proportion of fluoride intake was retained in the body. To assess the complex relationships among fluoride intakes, fluoride exposure, dental fluorosis, and dental caries, a cohort study started in 1992 in Iowa. The study recruited more than 1,000 newborns between 1992 and 1995 and collected detailed regular questionnaires concerning water sources, fluoride exposure, dietary intakes, and also conducted dental and bone exams. This study is still going on. The study found a considerable overlap in fluoride intake among those with and without caries and or fluorosis. They concluded that firmly recommending an optimal fluoride intake is problematic, and perhaps it's time that the term optimal fluoride intake be dropped from common usage. As mentioned before, several factors could affect the bioavailability of fluoride. For example, only 89% of fluoride in tea and 80% of fluoride in infant milk formula is bioavailable. And only 23% of fluoride in canned sardine is absorbed. Currently, in collaboration with Iowa University, we are assessing the availability of fluoride from different sources and its association with some health outcomes, including development of dental fluorosis and bone mass density. Finally, fluoride has been researched now for more than 75 years, but it continues to be an important topic for international discussion and further research. In 2018, a symposium took place in the US to critically examine currently accepted guidelines for fluoride intake in the population. Based on the current evidence, the symposium concluded that the current guidelines should be reconsidered. The symposium also highlighted the importance of dental fluorosis as the major determinant of adequate intake and the upper limit for fluoride intake. But they also emphasize the lack of agreement on what constitutes an acceptable risk. And therefore, there is a need for more detailed guidelines on fluoride intake to help inform policy. Okay. And thank you for listening, and I'm happy to answer any question you have. You can contact me by email and I'll try to get back to you as soon as possible. Thank you.